Hello, my name is Brandon K. Lee, and today I will be presenting the paper Neural-Machine Translation by Jointly Learning to Align and Translate by Dmitry Badanao, Kyunghyun Cho, and Yoshua Bengio, published in 2015. The agenda for this presentation is as follows. I will provide a brief history of translation techniques and then delve into the evolution of neuro-machine translation with machine learning before the publishing of this paper. From part 3, we will dive into the core innovation of the researcher's translational model and explain how the model works in its most basic components, the experimental design, and the results. Lastly, I will touch on the pros and limitations of this paper and the impact it has provided. Brief history. Have you ever wondered how machines translate sentences from one language to another with increasing accuracy? Previously, a rules-based system would be used to translate between languages crudely. Further improvements in the field led to statistical methods such as the traditional phrase-based method of translation shown on the screen. Each of these steps has slowly brought us closer to capturing the very essence and meaning of the original text that we were trying to translate. In the early 2010s, people started to ponder more about the process of translation from a probabilistic approach. The finding of a target sentence Y that maximizes the probability of Y given a source sentence X, as shown as argmax. So, this serves as the basis for the basic encoder-decoder approach that became used in neural machine translation. Here's an analogy. The encoder reads the sentence in the original language, word by word. Think of it like making a bead necklace, where each bead represents a word and the string running through them is a sentence's meaning. Within each word, the encoder updates its memory, like adding another bead to the string, ending up with a necklace that represents the whole sentence's meaning. This is our context vector. The decoder then uses this necklace to create a sentence in the new language bead by bead, or word by word, always referring back to the necklace to make sure that the translation fits the original sentence's meaning. The result? A translation that captures the essence of the original sentence, making sense in the new language. So, issues with this basic encoder-decoder approach include accuracy issues with longer sentences despite using long short-term memory RNN models to mitigate the Banshee gradient / short-term memory issues. The researchers also believe that the fixed length context vector approach created a bottleneck in performance and believe that the removal of such may be an option for further advancement. And lastly, this methodology does not capture how humans translate sentences by taking each sentence in its entirety and considering context to more accurately translate. So, finally onto the paper. The core innovation of this paper. So heart of this paper is in its novel approach to neural machine translation, a model that learns to align the process of determining which words in the source sentence correspond to those in the target sentence and translate simultaneously. More simply put, the model doesn't just translate word by word, but looks at the entire sentence, understands the context, and then decides the best translation of each word. The researcher utilizes this method of soft alignment between words of each language to further mimic human translation by allowing the model to consider the entire input sentence and determine the relevance of each word in the context of the whole sentence, rather than relying on a strict word-for-word correspondence. How the model works. In the new model architecture, the conditional probability is shown, where SI is an RNN hidden state for time I. It should be noted that unlike the original existing encoder-decoder approach, the probability here is conditioned on a distinct context vector Ci for each target word Yi. Let's break down how this model operates. The model starts with processing the source sentence with a bidirectional recurrent neural network. This means it has two RNNs. One reads the sentence from start to finish, and another reads it from finish to start. By doing this, the model captures the information from both directions for each word. This is similar to how we humans understand a sentence not only by the word we are reading, but also by the context provided by the surrounding words. The outputs from both directions of the RNN are combined to create a comprehensive representation for each word. This representation holds not just the meaning of the word itself, but also how it relates to the rest of the sentence. It's like having a full picture of what's being discussed rather than just a snapshot. When it's time to translate, the decoder, another RNN, starts generating the target sentence. However, instead of translating in isolation, it uses an attention mechanism. This mechanism looks at the encodings from the bidirectional RNN, decides which parts are the most relevant at any given time. As the decoder generates each word, the attention mechanism performs what's known as soft alignment. This means it doesn't just pick one word from the source sentence to translate. Instead, it calculates a weighted importance of all the source words. For instance, when translating the word it in a sentence, the model looks at all the words in the source sentence and decides which one gives the best clues about what it refers to. With each new word generated in the target language, the attention mechanism reassesses the source sentence, providing a dynamic, context-aware translation process. This dynamic aspect is crucial because the relevance of the source words can change depending on what part of the sentence is being translated. Experimental design. So the RNN model was trained for English to French translation with 1,000 hidden states, and its performance was compared to that of Moses, a statistical machine learning translator, serving as its benchmark. A model for their approach and the more basic encoding decoding methodology were trained on the two parallel corpora totaling 348 million words, which was later reduced to a short list of 30,000 most used words in each language. Each model was trained using this short list for 5 days, and performance was assessed via Blue Score in comparison to the Moses benchmark. On the figure, there are two types of models, the encoder-decoder and the search for the soft alignment approach. Both models were trained for sentences up to 30 words and 50 words. From the figure, we can see that the performance of the RNN encoder drops significantly as the length of the sentences increases. On the other hand, both RNN Search 30 and 50 maintain performance, with the latter showing little to no deterioration in performance based on the Blue Score. The table contains the Blue scores for all models compared to the benchmark of Moses. The superiority of the researchers' models is quite apparent, as their RNN Search 30 outperform even the RNN Encode 50. The asterisk RNN Search 50 was trained for even longer and was able to achieve a Blue score comparable to Moses when unknown words were removed. These figures are examples of the alignment found by RNN Search 50. Each pixel carries a weight of the annotation between each source word to the target word on a grayscale, with whiter areas representing a stronger match. This demonstrates what's happening under the hood when the model creates multiple variable length context vectors to better align and generate more linguistically correct translations. So pros and limitations. The pros of this paper was that a novel approach to neural machine translation was created that really started to mimic how a human translates. This allowed for more nuanced translations, such as idiomatic expressions. And I believe that this approach is adaptable to other languages too. However, the limitations for this approach that is very computationally expensive and does not handle rare or unknown words well. Overall, though, this paper didn't have any cons as it was a very well-designed experiment and meticulously written paper with a very novel idea. The overall impact of this paper was that there was a huge leap in machine translation of languages using this new novel approach as it mimicked the human's process of translation. It also served as a great foundation for modern neural machine translation techniques, such as the attention mechanisms in transformers. And lastly, it further spread research into AI and broaden the scope and application of RNNs. Questions? Thank you.